Hello everyone, my name is Shiva. I'm the first-year PhD student in Carnegie Mellon University. Today I would like to introduce our recent work, Super Odometry, IMU-centric LiDAR-Visual-Inertial estimator for challenging environments. For this paper, we mainly have following contribution. First, we propose the first IMU-centric sensor fusion pipeline that enables accurate and robust state estimation in challenging environments. Secondly, we combine the advantages of tightly coupled method with loosely coupled method. Thirdly, we evaluate our method in various challenging scenarios with aggressive motion, low light, and even in heavy dust environments. The main idea of our proposed method is that we believe the IMUs can be very accurate and robust as long as the bias drift is constrained by other sensors. Our work is developed in the context of DARPA subterranean challenge, which will help our robot to navigate internal, urban, and cave environments. Robust simultaneous localization and mapping is a fundamental need to achieve high-level autonomy for mobile robots. The question of its SLAM solved is often asked within the robotics communities. From my perspective, the SLAM problem is only solved in short-term, normal scenarios. It still easily fails under challenging conditions such as visually and geometrically degraded environments. Because of these challenges, our robots still find difficulty to achieve long-term autonomy. To solve this problem, we believe that an ideal SLAM solution should be fail-safe and failure-aware. The system needs to be aware of imminent failure due to outliers, degeneracy, or hardware failures. However, we found that most of the multimodal sensor fusion methods are unable to achieve this. In the last decades, multimodal sensor fusion has gained great popularity and can be classified as either loosely or tightly coupled method, as shown in the Table 1. Loosely coupled method has been preferred more because of their simplicity, extendability, and low computational expense. In contrast, tightly coupled method has proved advantages for their accuracy and robust performance. So why not combine these advantages together? Instead of combining all sensor data into a full-blown factor graph, Super Odometry divided the big factor graph into several sub-factor graphs: visual odometry factor graph, laser odometry factor graph, and the IMU odometry factor graph. For each sub-factor graph, it's tightly coupled-based method since it directly processes the raw measurements. While between the factor graph, it's a loosely coupled method since it only transfers the initial gas and pose constraints. Here is the overview of the proposed system. You can see that it's composed of three modules: IMU odometry, LIDAR-inertial odometry, and LIDAR-inertial odometry. The estimated states can be written as this equation: not only pose and velocity, but also accelerometer bias and gyroscope bias. Our system design follows a key insight. An IMU and its state estimation can be very accurate as long as the bias drift is well constrained by other sensors. Therefore, Super Odometry uses the IMU as a primary sensor. It uses observation provided by visual-inertial odometry and LIDAR-inertial odometry to constrain the accelerometer bias and gyroscope bias. In return, the constrained IMU odometry provides prediction to the VIO and LIO, which recover motion in a coarse-to-fine manner. So why IMU-centric SLAM? Why IMU-based SLAM? The major reason is that other sensors-based SLAM, such as LiDAR SLAM or visual SLAM, are environment dependent. Compared with these sensors, IMU is very robust and is not environment dependent and doesn't have too many outliers. Here is a comparison between IMU and visual camera. You can see that the only drawback of IMU is that it cannot achieve accurate estimation in long term. Because of this, Super Odometry regards the IMU as a primary sensor. The structure of IMU odometry factors is shown in figure, which is similar to traditional pose-graph structure. However, it's different, since the estimated state of IMU odometry not only contains poses, but also the accelerometer and the gyroscope bias. Each node in the pose graph is associated with a state. The edge between two consecutive nodes represents the relative body motion obtained from IMU pre-integration. In really degraded environments, VIO relative pose factor will have a lower weight. In contrast, in geometrically degraded environments, LIO pose factor will have a lower weight. Note that the IMU odometry can also incorporate the measurement from other sensors, such as GPS and wheel odometry. As long as the sensor can provide the relative pose to constrain the relative position and orientation of IMU pre-integration, these sensors will be fused into the system successfully. Okay, let me introduce our visual-inertial odometry pipeline. For front end, we track monocular visual features and laser point within the camera field of view, and use a laser point to provide depth information for visual features shown as Figure A and Figure B. For the back end, we minimize a nonlinear optimization problem that consists of visual reprojection factor, IMU pre-integration factor, marginalization factor, and a pose pariah from IMU odometry. The structure of visual-inertial odometry factor is shown in the Figure C. Remember that the IMU odometry can be constrained by other sensors. Therefore, when the environment is visually degraded, the IMU odometry pose factor will be dominant in the optimization problem. However, when the environment has good lighting condition, the visual factors will be dominant. Here is the structure of LIDAR-inertial odometry factors. We minimize a nonlinear optimization problem consists of a multi-metric SCP factor, IMU pre-integration factor, and IMU odometry pose factors. Multi-metric SCP factor will include the point-to-point, point-to-line, and point-to-plane correspondence. Similarly, when the environment is geometrically degraded, since the IMU odometry can receive the measurements from other sensors, the IMU odometry is still reliable, and the IMU odometry pose factor will be dominant in the optimization problem. Meanwhile, unreliable LIDAR constraints will be rejected or have a lower weight by evaluating the quality of constraints. On the other hand, when the environment is well structured, the multi-metric SCP factor will be dominant in the optimization problem. Here I would like to introduce how superodometry overcomes sensor degradation and adapt to various environments. Superodometry adopts a novel selective fusion strategies which automatically selects the most informative constraints. In normal tunnel environments, since there is no temperature difference in the environment, the thermal camera is degraded. We mainly use the constraint provided by laser and visual sensors to achieve laser visual-inertial odometry. In really degraded environments, you can see there are a lot of dust. We will use thermal camera instead of visual camera and achieve laser thermal inertial estimator. In geometrically degraded environments, you can see it's a long corridor. We will use thermal and visual camera to achieve visual thermal inertial estimator. Since superodometry uses multiple state estimation engine, it will distribute the sensor failure risk between several estimation engines. Therefore, it has more robust performance to overcome hardware failures and sensor degradation. One question arises: how to achieve self-fusion? How to decide if we need to switch sensor or not? For laser odometry, we combine the feature information matrix with 3D feature distribution together. We use inverse condition number to detect the degeneracy and use 3D feature distribution to find specific degenerate direction. In Figure A and Figure B, blue circle in the center shows the robot's position and the small red circles show the 3D features. Compared these two figures, it's clear that the feature distribution in Figure A may cause large position error since all the features are linked to one direction. For more detail, we refer you to read this paper. For visual odometry, we propose to use the feature tracking norm as well as two-freedom chi-square distribution to monitor feature reprojection error in a sliding window of VIO system. Since the special motion such as constant velocity, pure rotation, may also cause VIO system unreliable, we also monitor the motion of the robots to detect the degeneracy. Time synchronization is very tricky for multiple sensor fusion. The left figure shows the factor graph of traditional laser visual and IMU fusion. Since all the measurements should be ready at the right time, it requires very good time synchronization. Also, it fuses all the constraints in a single optimization problem. It's difficult to achieve real-time performance. In comparison, since all the subsystems of super-odometry can output 200 Hz and its relative pose constraint can be generated by using the linear interpolation method. Therefore, super-odometry supports sensor fusion asynchronously. Here I would like to introduce the experiment result of super-odometry in geometrically degraded environments. In this experiment, we run super-odometry in the long corridor environments. We compare the super-odometry with another famous work, Leo-Sun. You can see that the Leo-Sun began degraded in such environments because of lack of constraints in the forward direction. We can observe that there is a misalignment and a significant drift as shown in the yellow circle in the Leo-Sun. Super-odometry, on the other hand, can still work well since it uses visual constraints to estimate the forward direction. Here is a mapping result of super-odometry. You can see that the map is very accurate. We also test the super-odometry in visually degraded environments. In this data sequence, we hand carried the sensors and worked past a poor data room and combined with aggressive motion. The main image is mostly dark. However, super-odometry automatically rejects unreliable visual constraints and make use of laser constraints to achieve robust state estimation. Finally, we test super-odometry in both visually and geometrically degraded environments. In this experiment, the super-odometry was running with autonomous flight in cave environments. It shows the algorithm's ability to overcome airborne obstacles. You can see that both Loam and Leo-Sun fail to create an accurate map of the scene. Since super-odometry can select the most informative measurements and reject the outlier, it can still achieve robust estimation in the density environment. The build map is very accurate. The estimate trajectory is around 500 meters, and the endpoint error is only 5 centimeters. Here is a quantitative comparison between state-of-the-art method with super-odometry in previous challenging environments. It can be seen that the super-odometry is more accurate. Super-odometry also supports multiple platforms. Currently, it supports OS1, OS0, and Vanadai. It has been tested on UGV, UAV, and leg robots. Finally, let me summarize the main advantages of super-odometry. First, our IMU-centric sensor fusion architectures enables us to achieve robustness and extensibility, since it combines advantages of tightly coupled method with loosely coupled method. Secondly, I think super-odometry is simple and effective, since it avoids complex math to fuse multiple sensors. The reason is that the IMU has a simple and accurate probabilistic model. As long as other sensors can provide relative pose per to constrain the IMU pre-integration factor, these sensors will be fused into the system successfully. Thirdly, super-odometry divided the big factor graph into several sub-factor graphs, and each sub-factor graph receives the prediction from an IMU odometry. Therefore, the motion from each odometry factor is recovered from cost-to-find manner in parallel, which significantly improves the real-time performance. The key idea I want to share with you today is that we learned that the IMU is a very powerful sensor for state estimation. It can be extremely accurate as long as the BIOS could be constrained by other sensors. That's all for our presentation. Thanks for your listening.